science enthusiasts. I'm your host, Jason Sikowski. I'm a high school chemistry teacher, but you probably know our dogs, Bunsen and Beaker. They're the science dogs on social media. This show takes what's best from their account, the curiosity and fun found there, and swirls it into podcast form. Every week, we're going to take some deep dive into an area of science and look at the research that's going on with our pets. We'll also have an expert guest who will enthrall you with their area of knowledge. This is the Science Podcast. Hey everybody, welcome back to the Science Podcast. We hope you're happy and healthy out there. As I mentioned last week, I'm just going to talk about it briefly because people are a little worried. Yes, Alberta is having a very rough go with COVID right now. We're now under an entire provincial state of emergency in healthcare. It's kind of reached the point where there's just so many unvaccinated people in our hospitals that our system's close to collapse. We're actually sending patients to other provinces. Luckily, late last week, a whole bunch of new restrictions came in to convince more people to get vaccinated and protect the unvaccinated, I guess, from themselves. You know, we're hoping that helps and the numbers slow down over the next couple weeks. I don't want it to affect the kids I'm teaching because teaching online for many kids was the worst. Anyways, that's the update. On to the podcast this week. In science news, we're going to take a look at this amazing article that used powerful microscopes to figure out why insects can bite so hard based on the size of their little bitey bits, the mandibles. In Pet Science, an interesting study done by animal psychologists about cats looked at and found a bunch of different quote-unquote personality traits. So for the cat owners out there, you might find this really interesting. Our guest and Ask an Expert is Amanda Bachman, and she's going to talk to us about nuclear science. It's really topical as countries around the world are looking to move away from, fossil fuels, and one of the great alternatives that science needs to do a better job of communicating is nuclear. So we're happy to have Amanda chat with us. Hey dogs, did you know I tried to set up a nuclear power plant in my garage, but we were shut down by a games warden? Yeah, apparently we didn't have a fission license. Okay, on with the show, because there's no time like science time. This week in science news, it's all about the bite of insects. Now, I think we can all agree that we've been bit by an insect before, and it wasn't fun. I don't know what is happening with me now. This is off topic, but during the summer, I got stung by, I'm sure, wasps a couple times. Like, I've been stung probably hundreds, like over 200 times by bees or wasps in my life. Living on the farm, it's like an occurrence all the time in the summer because they make stupid nests in the ground and you disturb them and you get stung a couple times before you get away. I don't know what happened this time, but I had a crazy bad allergic reaction. And I went to the doctor, and the doctor's like, yeah, you know what? You probably need an EpiPen because the next time you get stung, you could die. And I'm like, great. That's a great development in my life. So when I saw this article about why, the science behind why biting insects or chewing insects have such strong jaws, I was a little intrigued, probably from a vindictive point of view, because I was so upset about my wasp stings this summer. To start with, scientists know that a lot of the chewing, biting insects, their bitey bits, the slashy parts, the mandibles or whatever else they have, are incredibly tough and durable. And previous reporting was pretty sure that they had actually metals infused in their bitey bits. A new study published this month in Scientific Reports took that a step further and really explained why they have such an incredibly sharp cutting edge. So physicists from the University of Oregon in Eugene and other colleagues around the world, the lead scientist Robert Schofield, used a really powerful microscope to take a look at the organisms' mouth parts, their jaws. And they started with leaf-cutting insects, leaf-cutting ants. This microscope was able to take a look at the atomic structure. So this isn't your ordinary bright field light microscope that is a magnification of 400 and you're like, wow, that's a cell. I can see the nucleus. We're talking about a very different type of microscope. And what they found was that on the biting, slashing parts of the ant's mouth, zinc atoms were dispersed homogeneously throughout the entire tooth, not a chunk, not like like a tip of zinc, the zinc atoms were throughout the entire tooth uniformly. And one of the interesting things when the physicists found this out is they talked to animal physiologists, and structurally they agreed this allowed the bitey parts of this ant to grow really, really thin or evolve thin, which makes them stronger, right? Think of a knife's blade. A knife blade that's really thin is going to cut better than an axe, for example, like a dull axe. And if you have chunks of metal, apparently, I'm not a physicist nor structural engineer, no animal physiologist, but apparently if you had chunks of metal, you wouldn't be able to, like the chunk of the tooth, like, I don't know, think of somebody gold plating their teeth. You wouldn't be able to make the mouth bitey parts as thin. The team then took a look at a bunch of different animals that have these metal-infused materials known as heavy element biomaterials. And they looked at spiders and some worms and like scorpion stingers. And they found that these metal materials were stronger and more durable than animals that had biomineralized materials. So that's like calcium stuff, calcium phosphate, like things in your teeth or your bones or sometimes the proteins on and the shells of an arthropod. That's really interesting because you think how strong our bones are, but apparently this biomaterial with the metal inside it, when they ran it through tests, it could take a licking and keep on chewing or ticking. The study goes into this conclusion is that it allows this ant to use 60% of the energy it would normally have to use without the specialized metal-infused biomaterial. This is the profound conclusion because this gets to the heart of why does a teeny tiny organism like an ant or something that bites you, why can it bite you so hard when it's so tiny? And the answer is their bitey bits are really thin, really strong, and it takes away the amount of energy that it would be required. So they need less muscle, need less insect muscle, and that allows them to be so small and do so much damage. I thought that was fascinating. Nowhere in the study did it talk about the stupid hornets that bit me in the summer or stung me. I still don't know. I know they can both bite and sting. I'm sure there's some kind of biomaterial there. Maybe if our teeth had the same metal-infused material that these ants do, we could just eat our way out of situations. Usually we eat our way into situations. That's what happened to me during COVID. That's science news for this week. This week in Pit Science, let's talk about cat personalities. Now, I'm going to have to go way out of my comfort zone. When I talk about cats, I know very little about cats. My family's never owned a cat. I'm allergic to cats. I can only be around them for a short period of time. I think they're adorable. I have no qualms or I have no beef with cats. I just don't know very much about them. And I know people who listen to the podcast don't have dogs, but they have cats. We've had guests that only have cats. Timothy Caulfield comes to mind that he loves his cats and he doesn't have a dog. So when I see something that talks about cats, I like to throw it into the podcast. I'm not sure if this is a study or is like a gathering of data that the University of Helsinki released, and they looked at a whole bunch of different cats, thousands of them, and different breeds of cats to try and develop breed-specific or cat personalities, quote unquote. And this strikes to the heart of a study I talked about a couple weeks ago, that we don't know enough about cats, or we don't study cats the same way that we study dogs. So it's interesting whenever scientists, actually take a look at cats. The impetus of the study by Hans Lohi is that cats, compared to dogs, have less information about how their behavior and personality can be unique or specific or common across households and breeds. So let's get right into it. This questionnaire was created by said professor. It was sent out to cat owners, and the total number of cats in the study was 4,300 with 26 different breeds. And across all of the different elements of the study, the questionnaire included a whole bunch of sections on background and health-related information. So getting like the background, where your cat came from, what its health is, health issues, but also other things like its behavior on a day-to-day basis. And these were the behavior traits that were identified by the study. And there's 7 of them. One of the behavior traits of a cat is how active or playful it is. Another behavior trait is its fearfulness. Another one is aggression. So that's 3. 4 is social ability towards humans. 5 is social ability towards cats. 6 is litter box issues. Okay, so I know what a litter box is, but litter box issues. And 7 is excessive grooming. One of the interesting things was I didn't know, again, I don't know much about cats, but the conclusion that all of these personality traits or these behavior traits are important to cats. They said that their first 3 were common in other studies: activity, fearfulness, and playfulness. But the ones that they identified that were new are the last ones, like litter box issues and excessive grooming. They found of the cats that were asked, I guess it wasn't the cats, it was the cat owners, the Russian blue was the most fearful, while the Abyssinian was the least fearful. And again, I know nothing about these cat breeds. Sorry. The Bengal was the most active breed. The Persian was the most passive. The breeds that had the most excessive grooming were Siamese. And then there were some other ones that were scored relatively low in social ability. And that's the Turkish van. So the idea is by gathering all this data, having these different personality traits, Lohi's group wants to take all of that data, and that's a lot of good data, to start to identify links between behavior and genetics, behavior and environments of concern and environments the cats live in, and any of those factors that lead to problematic owner-cat relationships. So do you think that's true? I would be really curious about this. When this podcast comes out, I'm gonna do a questionnaire. Do you think this is true? Do those 7 personality traits fit? Can you see that in your own cat? Let us know. Send me some messages through social media, but if you agree with this study. That's Pet Science for this week. Hey everybody, thanks for listening to our show week after week. If you want to know how to support the Science Podcast, here are a couple ways. It's always going to be free to download, so you'll never have to worry about paying for it. But, things do cost money running a podcast, and here are a couple ways you could help us out. One is join our Patreon page. It's amazing. It's growing. It's almost like an extended family. There's multiple tiers of support, and we have lots of fun perks for being part of our Patreon page. The other way you could support us is giving us an awesome review on Apple Podcasts or Google Podcasts, anywhere you can rate our podcast. Give us a great review. The third way you could support the show is checking out the Bunsen Burner BMD.com website. We have awesome merch there. We worked really hard finding quality merchandise that's comfortable with vibrant colors. And you'll find in limited quantities over the next couple months, maybe even less, the 2022 Bunsen and Beaker calendar. So 3 ways to support us: the Patreon page, 2, give us a great review, 3, head over to our merch stop and see if there's anything there you'd like. Thanks everybody. Now on to the interview section. It's time for Ask an Expert on the Science Podcast, and I have Amanda Bachman, who's a PhD student in nuclear engineering with me today. How are you doing today, Amanda?
I'm good. How are you, Jason?
I'm good. Where are you calling into the podcast from in the world?
So I currently live in Champaign, Illinois, so central Illinois, a couple hours south of Chicago, because I am currently attending the University of Illinois in Urbana-Champaign.
Okay. All right. And I've been asking people this question. I don't know really when to stop asking it. Are you and your family doing okay with coronavirus?
Yeah, as far as COVID goes, we're all doing well. I think everyone in my family is fully vaccinated. I think the bigger issue right now with my family is they all live on the Gulf Coast of Florida, or at least my parents do. And there's a tropical storm that's going to hit them later tonight, early tomorrow morning. So, just kind of got to batten down the hatches on that one to protect everything. But I think they'll be okay.
Right. Yeah. It seems like that area of the world down there, every year there's hurricanes and tropical storms, and you just roll the dice on how bad they're going to be some years.
Yeah. And you also roll the dice on just how many there are. We first moved to Florida in 2003. So the 2004 season, which was pretty typical, I think. A couple big storms, overall, not too many. And then you had the 2005 season where I think for the first time ever, we actually got into the Greek alphabet for storms. Naming storms, you go through the English alphabet, leaving out Q, V, X, Y, and Z, leave out like a couple of the letters, and then you get into the Greek alphabet if like you continue going. And then from there, from 2005 until like I graduated high school in 2015, there really weren't that many, especially that many that hit Florida. So we kind of had like a really long drought. And then over the last couple of years between Irma in 2017, and I think Dorian kind of did some stuff to Florida, if I remember right. And then now they're going to have Elsa come through. It's kind of picking back up again. And I think right now we can thank climate change for that one.
Yeah, that's what the climate scientists are saying. Especially that's what happened with the incredible heat wave that came through where I live in Canada.
Mm-hmm.
I don't know if it made news in the States, but we had temperatures in British Columbia and parts of Alberta that were the same as like the Sahara Desert for a couple days. And that's totally not normal. It's not normal for Canada to get that hot.
Yeah, I think I saw some headlines that like for 2 or 3 days in a row, there was one area of Canada that was like setting new records for the highest temperature in the country. And then I think there was like that entire town that burned down, unfortunately.
It was the same. It was very, very devastating. That same town that set those crazy records, it burned, 90% of it's burned down. So,
wow.
Yeah, we don't get the same kind of storms that you get, but we're still affected by some natural disasters occasionally. Anyways, let's talk about something more about what you're studying. So you are a PhD student in nuclear engineering. Could you go into a little bit of detail about what that is and why you're studying it?
Yeah. So my educational background, I have a bachelor's and a master's degree in nuclear engineering from the University of Tennessee in Knoxville. And so right now I'm pursuing my PhD in nuclear engineering here at the University of Illinois. So nuclear engineering is, in a nutshell, just trying to figure out ways that we can utilize nuclear interactions and some atomic particles to benefit people in some way. So kind of a fairly broad definition, but there's a lot of different facets of where you can apply nuclear engineering. One of the biggest ways we do this is through nuclear power, producing carbon-free electricity based on nuclear reactions. But there's also a lot of applications in medicine, in space exploration, and even in oil drilling. A lot of times you can use like nuclear imaging techniques in order to like find different oil fields. And so I am studying nuclear engineering. It's kind of an interesting story, and I think you'll appreciate part of it as a teacher. So when I was in middle school, my oldest brother actually started studying nuclear engineering when he got to college. That was the first time I'd ever heard of nuclear engineering, but, we're pretty close. He would talk to me about like what he was doing, what he was studying a little bit. And then I took my first physics course my sophomore year of high school. And at some point that semester, I was like really bored in study hall. And so I actually like started reading the physics textbook because, who does that? And like just reading through it, I was like, wow, this is fascinating science. It's, we sometimes describe it as like modern day alchemy because you're taking like one element and transmuting it into another element, which chemistry kind of says that you shouldn't be able to do that, but physics.
Yeah, no, you can't do that in chemistry. You're a crazy person.
Yeah, but physics definitely tells us we can, and we do it all the time. So it's just really interesting science. And that's, kind of when I was like, this is what I want to study. This is so cool. This is, literally blowing my mind. And I really continue to pursue it and, get these degrees in it because I really see it as one of the most powerful tools we have for impacting people's lives for the better, through any of the ways that we're doing it of producing clean power, producing reliable power, coming up with different imaging, diagnostic, and treatments for various conditions, especially cancer. So it's really just a gigantic force for good that I'm like, I need to be a part of this.
It's, when it's really been in the last, I'd say 5 years, there's been more talk about nuclear in where I live in Canada, right?
Mm-hmm.
for the longest time, probably because Alberta is an oil gas producing province, it was like burn all the oil, burn all the coal, burn all the natural gas, right? And everybody was pretty happy about that because it made Alberta quite wealthy. But now, of course, with climate change and a lot of countries having a push away from carbon, even though we'll never be really totally, devoid of using it, nuclear has been talked about quite a bit, and I want to know more. I want to learn more about it every day, and I'm just so thankful you're here talking to us about it. So one thing I liked how you said it was like modern day alchemy, because in chemistry, like as I teach high school chemistry, we one of the first things when we're teaching kids about chemistry when they're in grade 9, like younger kids, is the story of how chemistry came from alchemy, and alchemy was a bunch of crap, right? And literally people were trying to use like manure to turn lead into gold and all this crazy stuff. And I'm like, okay, so you cannot turn lead into gold. You cannot turn one element into another. And then there's always like some little kid that's like you that has been doing a bunch of reading, and they're like, what about nuclear fission? And I'm like, shut up, you. We're not talking about that. That's wrong. No, just be quiet, you. But then, I make a joke, but then we do talk about how you can do that in nuclear power, which is so cool. So was it really reading the textbook that got you interested in it and in pursuing a career in nuclear science?
Yeah, I remember like very vividly, actually. I was reading the textbook, and then I like closed it as just like a break, and then I was like, yep, this is what I want to study. This is what I want to do with the rest of my life.
That's so interesting.
So, I'm still here.
Okay, so I have a couple questions to ask you about nuclear power, since I've got somebody who knows what they're talking about instead of random people I ask. So obviously nuclear power is used for energy, for production of electricity. Could you tell everybody, could you break down maybe a little bit about like how much more power nuclear produces compared to other forms of energy? Like why should we be moving to nuclear energy, or why is that a good idea?
Yeah, so nuclear power, a lot of times a metric that we look at is energy density. So how much energy can you get out per mass of fuel? So it's, typically in units of like joules per kilogram. The energy density of uranium is phenomenally much higher than any other energy source that we have as far as like coal or oil goes. So for reference, when we talk about nuclear fuel pellets, these are small little ceramic pellets of, we use uranium dioxide fuel, so UO2. These pellets are a single pellet is about the size of like the tip of your pinky finger. So I think the weight of it is like 10 grams or something like that. It is a really small pellet. And we stack a bunch of these pellets into fuel assemblies, and then we put a bunch of fuel assemblies in the core. So we are using like a fair amount of mass, but the fuel pellets that we talk about are very, very small. And the amount of energy that you can get out of just one of those fuel pellets is equal to the amount of energy you can get out from a literal ton of coal, like 2,000 pounds of coal. And let me see if I can find the numbers here. I wrote them down for the others. And it's about 285 gallons of oil will produce the same amount of energy as that uranium fuel pellet, and about 39,000 cubic feet of natural gas is needed to create the same amount of energy as that one little fuel pellet, which you then have to take into account. Like nuclear power relies on, thermal energy systems. So you have to take into account thermal efficiencies, but that's similar for coal and natural gas plants as well. The other way that nuclear power is really efficient is the land use. So coal, natural gas, and nuclear power plants really don't require that much land for the actual power plant itself. If you compare this with solar and wind turbines, like you kind of need a fair amount of fair amount of land in order to produce a substantial amount of energy. So the amount of energy you get per like square meter of land is so much higher for nuclear than.
Oh, right. Like comparison to like, 1,000 wind turbines, you need like a field of them.
Right. Right.
Okay, cool. Yeah, that's incredible that that a little tiny pellet. Wow.
Yeah. And then I think Mairead mentioned this when she was on as well, but because we're using relatively so little fuel, one of the like fun statistics we like to give kids during outreach is if you produced like your lifetime's worth of energy just from nuclear power, the amount of fuel that you would need fits into like a soda can. It is really quite small. But that also means that by not requiring that much massive fuel, we can do a couple of things. One, we run our nuclear reactors for 18 to 24 months before they require new fuel. Versus like coal plants, you kind of need a trainload of fuel coming in every single day or every couple of days. So you don't have to worry about like continuously refueling. It's fairly robust to, during COVID, there were a lot of supply chain concerns for, various products. But that wasn't as much of a concern with nuclear because they weren't the plants weren't continuously needing fuel shipped to them in order to run. And the other thing.
Oh yeah, that's happened a couple times in Canada, actually. Mm-hmm. Like a big winter storm in Quebec, for example. There's all this like an ice storm, and it froze a bunch of stuff. And I believe, there is nuclear reactors in Ontario and Quebec, but they do use natural gas. They use like natural gas as a source of fuel, and that's shipped to them. And they ran out of it, and like they were in danger of.
Yeah, and we've seen that happen here in the U.S. some with like the different polar vortexes that have hit the Northeast. Sometimes like it just gets so cold that the natural gas lines like freeze, and so you can't get power, like you can't get the fuel to the plants. And so
maybe that's what happened. Well, yeah. I think it was both, actually. I think it was both supply and freezing.
Yeah. Yeah. So that's not something you have to worry about as much with nuclear power, especially since, at least in the US, when we do those refueling outages every 18 to 24 months, we try to schedule them for the springtime or the fall time. So when you're not dealing with peak winter demands or peak summer demands of energy.
Smart.
Yeah. Yeah. So the other big thing that the energy density of uranium lets us do is, it's relatively low waste. And especially since, the waste is a concern for some people with nuclear energy of, it's going to be potentially dangerous for a fairly long time after, it comes out of the reactor. But by volume, it is tremendously low. I think if you took all of the dry cask storage containers, which is how we store most of our spent fuel right now, if you took all of the containers that have been used to produce power in the US since, it started back in like the 50s, if you stacked them all into a football field, it would be like 10 meters high. So it's really not that much, especially for, we're talking about, what is that, like almost 80 years of power.
Mm-hmm. And it's tough you must get this too. It's tough to try to explain to people. You're like, yeah, that's a radioactive waste, and nuclear power does make that, and it is, there is a byproduct. But the byproduct of burning natural gas and coal is the stuff that we breathe in, right? Particulates and CO2, and it just the byproduct kind of just is part of our atmosphere and our lives, and it's invisible.
Right.
So it's tough to make that comparison.
Yeah.
But yeah, you make some nuclear waste, but you're also been breathing in all this crap for, a bunch of years, especially if you're in an area of the world that relies heavily on coal to make electricity.
Yeah. And you can think of it as, we know how much waste nuclear energy produces. Like we have to keep detailed records of it and, keep monitoring it for years to come, versus like, how, we have estimates on like, per, megawatt hour or so of energy that's produced by coal and natural gas, it will release an average of like these many grams or kilograms of different pollutants and CO2 and all that. But, we don't have maybe like a firm record of like, this many grams of CO2 have been released, this many grams of SOx or NOx. And then also, especially with coal plants, you have the coal ash,
particulates,
which kind of, sometimes will just be kept on site. And I know there's been a number of incidences where that has, gotten into different waterways and been a big issue of pollution for some local communities. We know how much waste nuclear has, and we will continue to know how much is there.
Interesting. Well, thanks for answering that question. That was that's a really great answer. And for everybody listening, it gives you a little bit more information about why there are some really big pros to nuclear power. I have a weird question for you. It's about nuclear fusion.
Okay.
Okay. Are we close to nuclear fusion, or is it like when, like 40 years ago, we were about the same close to nuclear fusion?
So before I get into answering that, let's discuss of like, what is nuclear fusion, right? So
sure. Oh yeah. That would be smarter than just jumping into it. Yeah, go ahead.
Nuclear fusion is when light nuclei, what happens in stars right now is fusion. And so it's typically like hydrogen. You'll have like two nuclei of hydrogen hit each other. And if they have enough energy and the conditions all right, they will fuse and form helium. And so this process happens because the rest mass of the helium and the larger nuclei that's being produced is less than the rest mass of the two individual like hydrogen atoms. So by combining together, you have a lower mass, and that gets converted into energy that's released. Knowing this based off of Einstein's famous E=mc² equation, so we can kind of correlate or equate mass and energy together. Right.
So that's the mass change times the speed of light sort of squared gives you the energy through this process.
Right. Okay. That like change in mass will also tell you, if it's exergic or endoergic. So similar in chemistry, you have exothermic and endothermic reactions, so that'll kind of tell you if a certain reaction will spontaneously occur because, it will be releasing energy, or if you need to put energy into the system in order for it to occur. Right. And so what we're trying to do with fusion is to, control those reactions and have those happen when we need them to. But one of the ways to make that happen is it has to be at really, really high temperatures. Right. And so when I say high temperatures, I mean like hotter than anything that's currently on Earth. It's kind of like taking the sun and putting it here on Earth into like a miniaturized form.
So like the plot line of Spider-Man 2. I don't know if you're familiar with the Tobey Maguire Spider-Man.
Yeah, is that the one with Doc Ock?
Yeah, Doc Ock makes the sun from tritium, and anyway.
Yeah.
Go ahead, sorry.
Yeah, and tritium is used sometimes in this process, with tritium being hydrogen 3. So it's a hydrogen nucleus that has one proton and then 2 neutrons. So that's where you get that 3 from. So you also have to keep in mind that for having fusion energy, we utilize plasmas. And I think this is like maybe not always taught super well in school. So plasmas are a state of matter similar to solids, liquids, and gases. What distinguishes it is you kind of have the electrons just like floating around and not strictly bound to a nucleus like what you have in the other states of matter. So in order to create these plasmas, that's, partially where that really high temperature comes in. And then you also don't have to worry about any kind of electron interactions to, change valence states and all that. And you can really just kind of focus on getting the nuclei to interact with each other. Since we're utilizing plasmas, they're at really high temperatures, we kind of need to confine them, keep them into like a certain shape. So that way it's, all staying where we need it to. And we do that a lot through magnetic fields, right? Because the electrons are still there. Everything is like kind of slightly charged since the electrons aren't strictly bound to a certain nucleus. So we utilize magnetic fields to kind of keep the plasmas in shape. And there's a couple of devices that we use to do this. One of them is called a tokamak, and the other one is called a stellarator. Right now, one of the biggest fusion projects in the world is called ITER, which is in France, and it's a huge international effort to try and, produce fusion. And that design is a tokamak. And the difference between the two is kind of like how they use the magnetic fields. I think tokamaks like pulse the fields, while stellarators have a pretty constant field. The other thing that you have to keep in mind is we're running these plasmas at really, really high temperatures. So that alone can degrade a lot of different materials because, thermal conductivity and melting points of different materials, especially since a lot of times we're using metals within these devices. The other thing that really impacts our ability to have sustainable fusion is the energy of the neutrons, right? Because we still kind of have neutrons flying around throughout this process as part of what's released in what's called a DT reaction. So deuterium and tritium fusing together to form helium-4. So you end up with like a spare neutron in there somewhere. And so through that process, your neutrons are released at 14.1 MeV, mega electron volts, which is incredibly high energy for neutrons. When we talk about fission for, the nuclear reactors that we have right now, uranium-235 fission events release neutrons at an average of about 2 MeV. So we're talking neutrons that are on average 7 times more energetic than what's released in our fission reactors. So you have a much higher temperature, you have a much higher energy of neutrons, and neutrons can really, impact your materials. They can cause, it's called, give me a second here, it's coming to me. We have the unit that you tend to use for material damage is called Dpa Displacements per atom. So for every atomic position within your material, so usually it's kind of a lattice structure of some kind, or if it's in a lattice, on average, how many times will an atom be displaced from radiation? And, there's self-healing effects within there to kind of fill in the gaps. So having, a couple DPA usually isn't significant and won't cause permanent structural damage to your material. But the higher energy your neutron is, the higher DPA you typically have because it can more easily knock an atom out of its lattice placement. So between high temperatures, high energy neutrons, you have a lot of different material concerns. So I think right now ITER is planning on using tungsten as some of its walls. And, there's been some work showing that as soon as you flip on some of these machines, that tungsten is just going to get destroyed because of the temperatures and the neutron fluxes and all that.
And tungsten is notoriously tough, right?
Yeah. It's what the most dense material on the periodic table.
It's got a super high melting point too.
Yeah. It's usually considered a very robust material. And
this process just annihilates it.
Yeah. So, there's a lot of reasons why we don't have fusion right now. And the main reason is it's hard. It's really, really hard to control these conditions, have materials that can withstand these conditions. So I think the joke within the nuclear community is fusion is always 20 years away. I do hope that at some point we get it all figured out and get the materials that we need to have fusion and have it be sustainable. So that way we have it as an additional clean energy source, because this isn't going to, release carbon dioxide or pollutants into the air. But it's definitely going to take a hot minute there.
So sounds like this is good for everybody who's like, oh yeah, we don't need to worry about nuclear fission. We're just going to wait for nuclear fusion. It sounds like it's a ways away from being
Yeah,
maybe never.
yeah, personally, I would definitely not expect fusion to be an option for the timeline that we need to accomplish a lot of these climate goals. So 2030, 2050, I would not expect fusion to be a viable option for meeting those goals.
Okay, well that's good. That's good for people to know. You read like the wrong article on the internet. Definitely, if you're not in the know, and it sounds like we're like on the cusp of having fusion reactors everywhere, like on top of your DeLorean. But it's not that way. So
we're not there.
Well, thanks for answering that question. That was great. Good job. The last kind of nuclear question I have for you is about how nuclear engineering, nuclear science relates to the medical industry. You wanted to talk a little bit about that. It's fascinating.
Yeah, this is, to me, the medical applications of nuclear science and technology is really just exploiting physics to like cure people. So a lot of people have probably experienced some form of nuclear medicine. We use it a lot for imaging. So if you've ever had an X-ray taken of your bones or your teeth, if you've ever had like a CT scan, I've had to have that one before. These all utilize, nuclear science in some way, and they're all based on how different types of radiation interact with different parts of your body, right? So for X-rays, they hit your skin, they hit your tissue, and they, are relatively unaffected. So they'll just go straight through, but then your bones have a higher density. And so they, react differently with the X-rays. And so they show up different in the images that we have. Another really big way that we use nuclear medicine is cancer treatments, right? So sometimes people like lump it as like radiation therapy, and that could mean a couple of different things, really. So a lot of times we'll use photons to treat cancer cells and try and kill the cancer, with photons just being a generic term for light or electromagnetic waves. Typically we do this with gamma photons. So if you recall back to science classes, you have the electromagnetic spectrum, organized by energy and wavelength. And so gammas are going to be your most energetic electromagnetic wavelengths, and they are going to have the shortest wavelength.
Right. So, they also, if you're lucky, they may turn you into a rage monster. That's the other thing that I know about gamma rays.
Yeah, in some
but I think mostly they just give you, if you're bombarded with them, they give you cancer and you die. So
yeah, so there's always the risk of certain radiation exposures having negative effects on the body, but nuclear medicine is making sure that we use those effects on the body in a positive way. So targeting cancer cells.
Right.
So we, shoot some photons into your body, targeting the cancer cell, and it will deposit energy there. And then, with enough doses, it will kill the cancer. Another treatment that we have that is really just fascinating to me, I've been able to, it's called Proton Therapy. And I've been able to tour Proton Therapy Center that's in Knoxville, Tennessee, from when I was there.
Oh, I've never heard of this.
Yeah, so this is really cool. So you create some protons, you speed them up in a cyclotron. So you spin them around, make them have a bunch of energy based on, using magnets and magnetic fields in order to speed them up. And then you shoot them down a beam line, and from that beam line, it goes into the person's body, right? So same idea as what we do with photon therapies of shoot the radiation into the body, targeting the cancer cell, and then use that energy that's deposited in the cancer cell to kill it. Also, what makes proton therapy so special is how protons, or heavy charged particles in general, react with matter as opposed to photons, right? So photons are going to kind of just like bounce around with electrons, and as they move through a material, just kind of slowly lose some energy as they go along. Heavy charged particles, because they have that charge and they are also interacting with the electrons, what happens is it'll kind of lose like a little bit of energy, or like deposit a little bit of energy into a material as it goes through. And then as it's losing energy, it kind of hits a point where it slows down enough to where it'll interact with a lot of different electrons at once based on how, opposite charges attract and all that. And so what happens is the energy that's deposited by a heavy charged particle as it goes through a material it's kind of constant. And then at some point it increases pretty sharply and then it drops down to zero. And so that's what's called the Bragg Peak. And so versus photons, it will like kind of continuously lose energy and it never, really like runs out of energy. It will always have like something left. Versus heavy charged particles will stop somewhere. And so by utilizing these particles to treat cancer, we can make sure that the energy from that Bragg peak is deposited inside that cancer cell. And so it's leaving most of that energy in the cell, and then it's also not going past the cancer cell. So you end up sparing a lot of the healthy tissue around the cell.
Oh, cool.
This makes a really big difference for, especially if you're looking at like brain or spinal cord tumors, where there's a lot of really sensitive tissue in that area. And so you want to damage as little of that healthy tissue as you can. So that's a really cool way we do it. Another method we have for cancer treatments that's still mostly in development, I think, is called targeted alpha therapy. So you have alpha particles, which is just the nucleus of a helium atom. So it's 2 protons and 2 neutrons, and it's largely going to be produced through just, radioactive decay. And so one of the isotopes that we're using right now that is an alpha emitter is called actinium-227. Oh, shoot, maybe it's 225. It's one of the actinium isotopes. I can double check on that. So what we do is we bind it to some different compounds and then like inject it into the body. And then because of those compounds that it's attached to, it will naturally go towards, certain types of cell. And so we can target it to where it's going to travel right to where that tumor is. And then because that actinium is naturally going to, decay and release alpha particles, it will release those alpha particles like into the tumor directly. So it's like a very it's called targeted alpha therapy. And so it's a very targeted way to address the cancer cells like right inside the body. And so I think there's been some really good success with that so far. And then they also, I think, are starting to look at ways to do this with beta particle emitting isotopes. So a beta particle is just an electron that's emitted from the nucleus during a decay system. And so beta particles and alpha particles will interact in similar ways with matter that's around them. With beta particles, since they are so much smaller in mass and have a smaller charge of only -1 instead of +2 for your alpha particle. So it can go a little bit farther. So that is also being looked at for slightly larger tumors. So that way it can, travel farther into the tumor and affect more of it at once, as opposed to the alpha particles. So a lot of different ways that we use nuclear science for medicine. And it really is just like purely exploiting physics. And it's so fascinating to me.
And it sounds like it's constantly evolving and changing, and
Yes.
There's new stuff on the horizon, which is really exciting.
Yes. And I think for a little bit there, Japan was also looking at using like a carbon nucleus, like a carbon-12 nucleus instead of protons, because it won't penetrate into the body as far, and it will also deposit more energy in a shorter distance. So if it's a little bit of a smaller tumor, that can be favored for, over protons based on the width of that Bragg peak.
Well, that's fascinating. It's instead of affecting the whole body, it's like a surgical strike almost.
Yeah. Yeah. It's a really good way to think of it.
That's cool. Well, thanks for sharing that about how nuclear science affects medicine.
Mhm.
There may be people that didn't know this before, and now they do. So that's great.
Yeah.
One of the questions we always ask our guests, that's a fun one. It's about pets. All of our guests get to chat about pets they've had in their life since this is the podcast. Do you have a pet story you could share with us?
Yeah. So my partner and I have a rabbit. He is very cute. He is a mini lop. So lop-ear rabbits are just the ones that have their ears like hanging down by their face as opposed to like straight back. His name is Röntgen. We call him Little R, and he is named after the physicist that discovered X-rays. Which Röntgen is also a unit of exposure when you like start looking at like dose. And then there's also like the Röntgen equivalent in man, which is like a unit of dose. So like pretty common name in nuclear science. So, but he's like black and white, like you would see like an X-ray image. So that's how he got his name. Yeah. So he has definitely been enjoying my partner and I working from home during COVID and the quarantine because he kind of just gets to chill outside of his cage all day. He has like a little cardboard box by the front door that he just sleeps in.
Oh,
yeah. So cute.
That's cute. He just hops around and sleeps in his box.
Yeah. And so one of the things that he started doing recently is he learned how to like hop up onto the bed in our bedroom. So he actually last night kind of joined me up there while I was watching some hockey and was just like having a good old time. He was doing what's called binkies, which is when a rabbit is like really happy and excited. They'll jump up like pretty high in the air and like twist their back feet around and kick around. It's really cute. So if you ever see a rabbit doing that, they're just really happy.
And so, it's called a binky.
It's called a binky. Yeah.
Even the action is adorable. The
right. But yeah, so he was
cute. And how long have you had Röntgen for?
We've had him for almost 2 years now.
Okay.
So cool. Got him August of 2019. So we've had him this whole quarantine, and he is
he's a COVID bunny.
Well, we got him like long before COVID.
Right. Yeah.
Definitely made COVID a lot easier to handle when you can just like kind of look down and you're like, oh, that's a cute face.
Yeah, pets have been the unsung hero of the COVID time for sure.
Yeah.
Well, that's cute. Thanks for sharing your pet story. The other question that we always ask our guests for is the super fact. And the super fact is something that you know that when you tell people kind of blows their mind a bit. And I know for people listening, their mind has been blown with your nuclear science. Do you have a super fact for us?
Yeah, so usually the ones I go to, I've already brought up in the show of like how energy dense uranium is and like how little fuel we need to like power a person's life. So there's another fact. So I was kind of earlier talking about how photons interact with matter. And so there's 3 main ways that like we kind of care about as nuclear engineers. So the first one is the photoelectric effect. Which is what Einstein got his Nobel Prize for, was his work on the photoelectric effect. So if you can kind of think about this like in terms of billiard balls, right? So you have your incoming photon will strike an electron and it deposits all of its energy into that electron, and that electron is ejected from its orbital, and the photon no longer has any energy, so it just kind of goes away. So in terms of billiard balls, one ball comes in, strikes another one. That first billiard ball just kind of stops, stays there, and then the other one goes off with some energy. Another way is Compton scattering. So instead of the photon depositing all of its energy into that electron, it scatters off with some energy. So in terms of billiard balls, your first one comes in, strikes the second one, your second one goes off, but then your first one goes off at a different angle, right? The one that's really mind-blowing is this third method called Pear Production. So you have a photon come in, it interacts with an electron, and then you actually get an electron and a positron out, and the photon just kind of disappears.
It just goes away.
Yeah, it just goes away. So then you start with a photon, and then you end up with just an electron and a positron, with the positron being, the antiparticle of an electron. So same mass, magnitude of charge, but the charge is positive now. And then what's even crazier is then with positrons being antiparticles, they then will interact with an electron that's around it and then produce more gammas. So you get like photon to particles to more photons. And I think that's just kind of crazy how it all happens.
It is like alchemy.
Yeah.
Oh, that's mind-blowing. Very cool.
Yeah.
I'm not smart enough to ask a follow-up question, but I that's very interesting. Very, very cool.
Yeah.
Thanks for sharing your super fact.
Yeah.
The last section of the podcast is a fun one because we get to know you a little bit more as a person. It's the what you're passionate about section. And you are so passionate. Your passionate section is still about nuclear science. About advocacy for nuclear science? What did you want to talk about there?
Yeah, so it's specifically with regards to nuclear energy and, understanding how important it really is to, communities and our energy markets. So this is something I've really been kind of battling with over the last year living in Illinois. Illinois has 6 different nuclear plants, and we get over half of all energy from these plants. It's about 54%.
Wow.
And there's 2 of these plants that last fall, the utility announced it would, seek to prematurely close them just because of economic conditions. They're not making enough profit. And so they were going to, seek some subsidies from the state in order to continue operating them and not, just be hemorrhaging money. But if they didn't get those subsidies, then these plants would close. So unfortunately, we have seen a fair number of nuclear reactors close in the United States over the last couple of years. I think when I started college in 2015, we were at about 103, 104 nuclear reactors, and now we are at about 93 reactors. So we've lost about 10 reactors in the last 6 years or so. And when you close a nuclear reactor, right, so these are very large power plants, usually they're around 800 to 1,000 megawatts of energy. Compare that to, a lot of times coal and natural gas plants will be about like 400, maybe 500 megawatts. And then your solar and your wind turbines are going to be a fair bit lower than that. So if you close down a nuclear plant, you lose a substantial source of power, and you also lose a substantial source of clean power. And so we've seen it time and time again, where if you close down a nuclear plant, everyone's like, oh, we'll just replace it with renewables. Well, you can't really replace that much energy with just renewables with the current technology we have. So most of that energy actually ends up being made up through fossil plants, natural gas a lot of times. We saw, was it earlier this year, Indian Point 3, Unit 3 closed in New York, and they explicitly said, like, we're going to build new fossil plants in order to replace this energy. So you're really having a much dirtier energy grid when you close a nuclear plant. And so just over the last year, I've spent a fair amount of time talking with the offices of my state representative and senator, trying to raise awareness of like closing these plants, like whether you agree with nuclear energy or not as like, the solution for solving all of our issues. Or, we have seen time and time again that like closing these plants is antithetical to any of the goals we're trying to establish for ourselves. So I would encourage people to, if there's a nuclear plant near you, make sure that you contact your elected officials about how much that means to you and how much you care about the clean energy they produce. And then also, see if there's any way that you can encourage the building of new nuclear plants. There's 2 reactors currently under construction in Georgia, but that's all we are building for nuclear plants right now.
Is it just cheaper to build the fossil fuel plants, or is it more political?
A lot of it is economic. It is cheaper to build the fossil plants, and then it's also usually a much shorter time frame to build them. Like you can
Right. I remember reading that. Like it's years to build a nuclear plant versus like half a year to build the fossil plant.
Yeah, something like that. I think it's still like maybe a couple years for a fossil plant, but nuclear plants definitely take like closer to a decade is what we're seeing right now with the plants in Georgia.
Wow, really? A decade to build? Is that just because they have to have all of those redundant safety stuff in them or just more complicated to build?
A lot of it is the safety and the licensing. For the project in Georgia right now, I think they've run into some issues of like, we haven't really built nuclear plants on a large scale since like the 90s. So a lack of continuity of knowledge. There were also some issues with like cash flow for the project. And so I think one of the main people actually like declared bankruptcy, and it was a whole thing. So a lot of things that were going into play for that project specifically. But yeah, in general, it takes a while to build a nuclear plant, partially because there's so much concrete that you have to pour. And it has to be like the right type of concrete as well, based on the regulations.
So it seems, so I remember reading that. So that's a tough thing. Hey, is that convincing? It's like humans are just so bad at planning long term, right?
Yeah, and we're seeing some different states and utilities that they're like committed to clean energy and whatnot, and so some of the ways that they are following through with that as far as action goes, there's Duke Energy just filed for a license extension on one of their nuclear plants. So, they're licensed to run for so many years. So getting a license extension will allow that plant to run for an extra 20 years. So definitely, keeping the clean energy that we have online will definitely continue to help us get closer to that goal of, net zero carbon. And then there are some states and utilities that are really looking at advanced reactors. So new technology that we don't currently have deployed commercially. Came out pretty recently that like the state of Wyoming is going to work with TerraPower for siting and then building one of their reactors. I know TVA has looked at some different advanced reactors for going at the Clinch River site near Oak Ridge. So, looking at new ways for us to deploy clean technology that, will be a little different, be a little more flexible because they're going to have lower power outputs. So, if it's a smaller community that only needs a couple hundred megawatts as opposed to, an entire gigawatt, like some of these large plants are, adapting to what communities need. So a lot of positive, optimistic things on the horizon, but we'll see.
Well, it's good. Information is power, right? And that's yes. The idea is you until people know, they don't know, and then they'll make decisions about what they know, and maybe they don't have all the facts. So right. That's good work on your part. Thank you, and thanks for sharing that with us on the podcast today. We're at the end of the interview. This has been such an enjoyable chat. I've been fascinated, and I've learned a lot, and I hope the audience has too. Where can people find you on social media? Do you have a social media account or a website? I do have social media. So I'm really just on Twitter. You can follow me at Amanda_Bachman, spelled the same as my name. So pretty easy to We'll
find
have that
there.
in the show notes for people to click on.
As an extra plug here, so I also would recommend following U.S. Women in Nuclear. It's a professional society that I'm fairly active in. So they work a lot with like outreach to, talk to the public about nuclear science and technology, but then also like kind of looking inward in the industry of, how can we close some of like the gender gaps and have more inclusive industry. And so they also focus a lot on professional development to accomplish some of those goals. Nice.
Okay, we will have that organization in the show notes as well.
Thanks.
Thank you again for giving up your time to talk nuclear with us today. You will be a great advocate for nuclear power in the future. I can't wait to see what your career turns into.
Oh, thank you. Appreciate that.
Okay, it's time for mailbag. But it's time for the mailbag. If you don't know what mailbag is, it's when we ask you questions on Twitter and then we answer them on the podcast. So we put a poll up on Twitter. Questions are about doggy daycare, free-range chickens, beaker training, and that's it. Doggy daycare, free-range chickens, and beaker training. I will talk about the free-range chickens, even though it wasn't first. It came in second. So basically, what's going on now is the chickens started escaping because we have like picket fence, which is just like wire going around on the grass a little bit. And then the chickens go inside of that and they chill out most of the time. But recently they've been escaping, but we fixed the hole. And really, we didn't really need to do anything with them. But what we did do is we just opened the door and we let them just walk around. So now we just have free-range chickens everywhere. And all that they do is just they dig holes in the ground and then lay in them all day. I don't get... chickens are kind of... If you don't know, chickens are kind of dumb. They're not the smartest of creatures. So I guess that's a pretty entertaining thing for them to do all day, is just dig a hole and then lay in it all day. You know, that sounds a bit something like Bunsen would do. But yeah, that's all about the free-range chickens. Mom, what are you going to talk about?
It looks like I'm going to talk about doggy daycare. So the dogs get to go to doggy daycare every 2 weeks on Tuesday. And we do that so that they can familiarize themselves with other dogs and have a chance to play all day and have fun in another environment. And that's why they go to doggy daycare. The doggy daycare that we are currently taking the dogs to is called Lacey and Foxy's Playground, and the dogs have a great day, and we really love how they take pictures of the dogs, and we can creep on them on Facebook, and Beaker is always smiling and always cuddling and wanting to get into everybody's laps. And when I dropped them off last Tuesday, she was like, "Oh, hi." And Bunsen was just standing in the waiting room, but she went behind the desk and I said, "Hey, you've got a little lab assistant."
Dad, what are you going to talk about?
So today's was a long day, but it was a good day. Beaker passed her first, actually the second level of obedience training with Waggles Academy for Dogs in Red Deer. We had to run her through this really cute obstacle course, and she did amazing. I flexed a little bit on the other dogs that were there. Beaker and I flexed a bit. We had to do a 10-second focus. And then after the focus, she high-fived me because we trained that. It was like a little routine. And everybody was like, what the heck? Because all the other dogs were just struggling a little bit. And Beaker just nails the 10-second focus with a high five. It was a little bit of a flex. So, as Adam always says, she's so smart, and I say she's got a brain like a computer, so she's obedience training. So we're really proud of her. A couple more questions in the section were about the videos that we shoot with the dogs, like the Beaker bracket and Bunsen and Beaker Teach Science. And that's on my docket to get back to doing those things. Comic-Con and being a cosplay guest was kind of all-consuming for about a month. I had to get so many things ready for that. And then, because Chris and I are teachers, we're back to school. And with COVID and just start up at school, that's also been super chaotic and really busy. Adam's also been really busy, and we need all three of us at the same time to shoot the Bunsen bracket. But we're going to get back to doing that now that a bunch of stuff isn't as busy. So, yeah, and I'm hoping to shoot some more Bunsen and Beaker Teach Science. All right, back to you, Adam.
Completely unrelated. The dogs really like peanut butter. Anyways, that's the end of mailbag. I'm now closing up the mailbag. And the mailbag is now closed. Thank you so much for answering on the poll and putting your questions down in the comments. We might get to those in a different episode of the podcast. But yeah, until next time, bye-bye.
That's the end of another Science Podcast episode. Thanks for tuning in every week to our fun and hilarious show. Special thanks this week to Amanda Bachman, who talked to us about nuclear science. We'd also like to give a special shout out to our top tier patrons on Patreon. Without their support, we wouldn't be able to do what we do. If you want to hear your name at the end of the podcast, head over to the Patreon page and sign up. Take it away, Chris.
Samantha Dodd, Kimberly Bond, Nate Stevenson, Debbie Anderson, Courtney Proven, Renee Hardy, Mary Rader, Shelby Leggett, Dan Fry, Mary Coos, Katla Lynch, Marianne McNally, Andrea Persons, Elizabeth Bourgeois, Karen Beth St. George, Bianca Hyde, Lynn Armstrong, Lisa Swartz, Catherine Jordan, Donna Craig, Lila Ashier, Jody Ogren, Liz Button, Kathy Zerker, and Ben Rathert.
Let's close with the dog's motto for science, empathy, and cuteness.